So yesterday I was talking about some basics on the hyperbolic space, and at the end I was talking about projection from one geodesic to another, and through something called bounded projection. But I was quick at the end, so let me start reviewing that fact. So the setting was X was the hyperbolic space, and the group is acting on X by isometries. And I assume the action was proper. And I fix, and then I assume there is at least one hyperbolic isometry, at least one hyperbolic isometry. By definition, it has an axis. It's an axis. Got it. Okay. So example you should have in your mind is that so G is pi1 of a closed, say, hyperbolic surface, and then this acts on the universal cover, which is hyperbolic plane. And any non-trivial element in here is hyperbolic on this. So that's that was the second. So this is H2, and you have axis gamma, and G is acting like this. Then I call it lemma. Lemma is that the existing constant L such that for any, so now I look at the translate of this axis by another element. Well, if you happen to take G, of course G gamma is gamma, but typically you get another geodesic. For any, and you project from A gamma to gamma, that's the nearest point projection. So it's going to look like this. This is the projection. And the claim is for exists a constant L for any A on either. So what do you guys say? Okay, either A gamma is parallel to gamma, that means house of distance between A gamma is finite. And of course in this case, if you project A gamma to gamma, then you get nearly everything. So in this case, diameter, the projection of A gamma to gamma is infinite. Okay. Or the projection is bounded. Diameter of the projection is at most L. So this was the claim. And in this case, in fact, okay. So anyway, this is a claim. And let me review the argument. So suppose the projection is big. It's very large, which I decide later, but very large. And I like to say that A gamma is parallel to gamma. But in the argument, what I have shown is that, in fact, there exists an integer, positive number k, such that gk, so gk or g minus k. So before proving, or to prove A gamma is parallel to gamma, I actually show this algebraic condition, namely G, well, some power of G is conjugate to itself by this element A. And then from this you can easily show that A gamma is parallel to gamma because this has axis gamma and this has axis A gamma, and actually it's the same element, therefore those two geodesic axes form a same element, and therefore they are parallel. Okay, that was the logic. And the proof was this. So you have gamma, a large projection, you remember, so A gamma, if it had a large projection to gamma, actually because of their hyperbolic geometry, they don't stay far away for a long time. The picture is, if it has a large projection, it's gonna look like this. That's the only way for A gamma has a long, large projection to gamma. Okay, so this is really a projection. Okay, if you are familiar to the geometry of the tree, just imagine you are in the tree. Then this is a picture, exactly coincides, and this is a projection. Okay, so this is very large as a projection. And yesterday I take point P here, but maybe today I take point P here. It would be maybe easier for you to understand. So the action of G is like this, and let's assume, to be concrete, the action of AG, A inverse, is in this direction. It could be reverse, but to fix the idea, and then at the end, that's how you get G to the K or G to the minus K. Let's assume that AG, A inverse translate A gamma the same direction as G does to gamma. Okay, so now I apply G to the N to P, then you get another point on gamma, and since I'm assuming this projection is so large, so for a while, so you get GP, G squared P, and for a while you get those points G to the P on this projection segment. Okay. Now, since those two geodesics stay close, so there must be a point Q, which is not so far away from G to the N of the P. And if gamma is a geodesic, then remember, if they stay close for a long time, actually this distance is at most 2 delta. If gamma is just a quasi-geodesic, maybe this is slightly bigger constant with a control. So let's assume this is a geodesic for the moment. And then those two distance between those 2 points is at most 2 delta. Now I apply AGA inverse. So I start moving this point Q back to P. And then if I apply, you have to think a little bit, but if I apply this element or inverse of this element n times, you're gonna get point AGA inverse minus NQ around P, because the same translation lengths. Okay, and now okay, so this point is exactly on this A gamma, but if I apply this element to G to the N of P, it's gonna be maybe here. So just AG A inverse minus N G to the N P. Okay. The point is this distance is also at most 2 delta, because this is isometry. So this is the distance is at most 2 delta, and this distance is at most 2 delta. And this distance, not exactly 2 delta, but something like 5 delta or 4 delta. Therefore, this point is in the, I think yesterday I claimed that in 10 delta neighborhood of P. Okay. let me write this bond. This is like, say 10 million. Okay. So the conclusion is I apply g to the n to the p and apply AG inverse minus n to p, then I always get the point in this yellow ball. Okay? But now I use the properties of the action. So the conclusion is p minus AG inverse minus n g to the n p. Okay, for any, okay. This is what I get. This capital N, you can make it as big as you like if you assume this constant L is very large. Okay, if it is very long, then you can apply this G many times. Okay. Then now eventually, since the action must be proper, there are only finitely many group elements which can satisfy this. Therefore, eventually, if this large n is too big, then by pigeonhole argument, for different little n and n prime, you get the same element. From this, you get AG A inverse minus n1, g to n1 is AG A inverse minus n2, gn2. So n1 and n2. Eventually, you get this this equation. Okay. I repeat it again. So there are only finitely many possibilities for this element. Therefore, if this n is very large, you're gonna get this equation. Okay. And from this, I did it. You can get this in Tohoku. Actually, in this case, k is I think n1 and n2, and the direction matches up. I think you get this one. Okay. So that was the argument. Hope it's better or clear today. Okay. So let me go on. If you look at this argument carefully, or as I did, so I didn't, the position of P was not very important. It could have been here, or it could have been here. Okay, so what I want to say here is that it's not only about one point. As long as this projection is large, in fact, this element nearly fixes the whole segment. Okay, so I just do the same trick. So I just write it in here. So in fact, so let me write this. This is true for nearly for a long subsegment of the projection. Okay, it doesn't have to be this point. I mean, this point is also true. So therefore, there is a chance for you to make the assumption the action was proper weaker. Okay. So in view of this observation, now I define slightly weaker property for properness of the action, which is called weak proper discontinuity. By the way, I have using the term proper, but I could have also used discontinuous, which Alan used in his talk. So it's not really important then. But anyway, we proper discontinuity. So let me write down the argument. So my point is that if you look at a long segment, if you fix a long segment on the axis, And if you look at all group elements which doesn't move any point of the segment very much, then it's going to be finite. So that's weak proper discontinuity. So let me write it formally. So group G is acting on some, well, built hyperbolic space or some geodesic space by isometry, and G is a hyperbolic isometry with axis gamma. Then I say G is a weak proper discontinuous element if she's going to be any R exists L such that any X and Y on gamma with the distance at least L. If you look at the element in G, well, maybe A is A such that X is A doesn't move X very much, which is R, and is finite. Okay, so this is a definition of the WPD element. So I'm not assuming that the action is proper. If the action was proper, any element is WPD, because the picture is that, so you have gamma, the axis, you take 2 points, X and Y, which is far enough by this, quantified by this constant, and if you look at R ball, the constant R is given, and you look for all group elements A, which move X into this ball and Y into this ball. Okay? But if the action was proper, you only have to look at 1 point, say X, then it's already finitely many. But here, it's weaker. I look at sort of action on a pair of points, which is far away, then that action is proper. That's what it says. Okay? But now I go back to this case, and as I told you, I could apply this argument to any points, nearly any points on this segment, and if I assume this segment is large enough, if my element G was a WPD element, even if the whole group action is not proper, I could run this argument and conclude the same thing, namely namely bounded projection. Okay, so let me write it as a proposition. So better proposition, well, actually it was maybe lemma, is so X delta hyperbolic, G acting on X by isometries, and G hyperbolic and WPD and gamma axis of G, then bounded projection is true, namely existence of constant L such that for any element A in G, either A gamma is parallel to gamma or projection is bounded. So it's weaker. The assumption is weaker. So in that sense, it's better. Okay. So that's one additional little bit sort of improvement of the lemma.
Could you give me an example of where your lemma is not acting properly or weakly?
Sure, I do it now. Okay. Yeah. I think a very easy example. Yeah, well, let me explain the example. We notice this property. Okay, so this is the curve. Well, this is a... So maybe it's good time for me to explain what curve complex is for a surface. So S is a compact, orientable, connected surface. Maybe possibly with boundary, but yeah, okay, compact, so boundary components of finite many. And how we define a complex, and in this case I'm just talking about one skeleton of that, so I call it graph, which is called curve graph of the surface, is the following way. So the curve is a graph. So to define a graph, I have to specify, I have to say what the vertices are and how to join them. Okay. These vertices are the homotopy class of essential simple closed curves on S. So essential means not homotopic to a point or into the boundary. So, well, I just if this is a genus 2 surface, then for example, like this, or those are essential simple closed curves on S, and if you just look at the homotopy class, each of them, alpha and beta, defines a vertex in this curve graph. And two vertices are joined by an edge if they are disjoint. Well, to be precise, since it's a homotopy class, so if you can take some representative in the homotopy class which are disjoint. So in this case they are disjoint, so you join. So this is the vertex for alpha, and this is a vertex for beta, and in this case they are joined in the curve graph. So that's also an essential simple closed curve on the surface S, and so they are, it's not homotopic to alpha or beta, so it defines another new vertex of the curve graph, and since alpha and gamma are disjoint, I join in the graph, and gamma and beta, where intersection number is 1, so whichever representation you take, it has to intersect, so I don't join gamma and beta. So this is just really a part of the whole graph. Okay, so this is the definition. And of course, if you just take the block complex that Mike was talking about, you get some complex. That's a complex of graph. Sorry, complex of groups, complex of curves. Well, here's some remark. In fact, if genus of surface is small, to be precise, less than or equal to 1, you may have to modify the definition, because because, for example, torus, if you take any two non-homotopic curves, they have to intersect. That means this complex is going to be just a disjoint, any disjoint point. So in this case, you change the rule when you join two vertices. So join alpha and beta if, say, number of intersection is 1 or maybe 2. It has to be a least number of the intersection. In other words, in this case, the number of this intersection is 0, then you join. But in some low genus case, you need to modify. So, but that's a couple or a few exceptional cases. Okay, and but in that case, a good point is that you have a sort of complete description of the curve graph. Namely, if S is torus or torus minus 1 point or sphere minus how many points do I have? 4 points. Then this curve complex is in fact a Faraday graph which appeared in Sunny's talk. Which was, well, in her talk, she was talking about ideal triangles, but in here I just make those ideal triangles into the real one, so it's okay. Then here's the theorem. Minsky says curve complex is delta hyperbolic. Namely, the triangles are delta thin. Okay. And moreover, because of this construction, so mapping class group of the surface acts on the curve complex in the canonical way by graph automorphisms. So mapping class group of the surface acts on by isometries. Well, so mapping class group is a homotopic class of a homeo from S to S, and of course if you have a simple closed curve, if you apply homeo on that, you get another simple closed curve. In that way, mapping class acts on the curve complex, and clearly because of the way I constructed the graph, this is automorphism. So therefore, it preserves the distance by isometry, and so the element is hyperbolic in the sense I defined yesterday, namely there is a invariant quasi-geodesic if and only if G is pseudo-anosov. Well, if you're not familiar to this kind of terminology, well, there is a classification of elements for mapping class group elements, and this is a typical one. And so the theorem says that typically your map is hyperbolic. Okay, so you have a group action by mapping class group on some delta hyperbolic space, but the action is not proper. Okay, so because it has an infinite stabilizer of a vertex. To see that, well, I still have a picture there. Yeah, well, I draw the same picture now. So you have alpha, and this alpha is a vertex in the curve graph, and the stabilizer of this matrix is very large. In fact, mapping class group of the subsurface which you obtain from S after you remove alpha, the stabilizer is the mapping class group, the surface you remove alpha. Because if you have a mapping class which preserves alpha, well actually, yeah, okay, you can. No, but my point is, whatever you do on this right-hand side of the surface, it doesn't move alpha at all, therefore it's a stabilizer. But this, because mapping class group of this subsurface is usually infinite, therefore the action is not proper at all. It's an infinite stabilizer of the point. But okay, now I come back to the question by Sunny. So is the proposition.
Maybe in the definition of corporate, the vertices should be KAIST because
Yeah, you're right. So what bothers you?
not KAIST.
It's same on the surface. That's a fact. Yeah. Yes, isotopic glass is fine. Yeah. Okay. So what do we know? The little proposition here is what I have shown with Vestimina. For the action of mapping class group of the curve complex, any G pseudo and also is WPD. Okay, in this sense. So if you look at 2 points, in other words, if you look at 2 curves far away on the axis, then there are only finitely many elements which don't move those 2 points very much. Okay. Therefore, this bounded projection lemma holds for the action of mapping class group of the curve complex. Okay, so this is well already half of my talk, but this is the end of the sort of review and some additional properties for this kind of bounded projection thing. Where?
And use proposition.
Yeah.
Here is
Any element which is Susanov is WPD. Sorry. Which is that is Susanov is hyperbolic by Razor-Minsky and WPD in this sense.
so WPD is another property of a group or
No,
just
about each element. Well, it's about the group action, but it's about each element. Some element is maybe WPD, some is not. Yeah, per element-wise property. But in this claim is any Susanov is WPD. Although the whole action is not proper. Okay, so I start a new section. And this is the theme of this lecture. So let me go back to the standard example. You have hyperbolic surface and which acts on the universal cover. And in this case, again, the action is proper, and you fix one hyperbolic isometry and an axis gamma. Okay. All right. So this is a setting. Okay. So now as yesterday or beginning of the talk today, I look at the translates of this axis gamma by group elements in G. So you get. By the way, if I didn't have to start with a simple closed curve on the surface, therefore maybe they intersect, but the picture becomes messy. So I draw them disjointly. Okay, so let Y is a set of all translates of this axis gamma. So this is some set. So this is if a gamma is B gamma, I see it as one point. So this is, in that sense, this is not exactly precise, but I look at all translates of gamma. That's my set Y. And of course, G acts on Y by the definition. And for each Y, for each element Y, we have a projection. This nearest point projection. Okay. So previously I have been talking about the projection to gamma, but of course we can project to any translate of gamma. So that's pi y. So this is the nearest point projection. And because this action was proper, so it has a bounded projection property. So has bounded projection for with constant L, like this. And this L is good for any translate because essentially you get the same picture. It doesn't matter if it's about 2 gamma or a gamma because it's really the same picture. Okay, now I define some number in the following way. So we now define so this Y and A and B are Y, and I assume Y is in A. The picture is, so you have, say, Y here, you have A here, and you have B here, and you project like this. And I'm looking at the diameter, the projection, so this is the number I'm looking at. Okay? Well, so this is a finite number. Because, I mean, since, well, so in this case, so what does bounded projection say? As long as those two geodesics are different, the projection is bounded by L. Because in this particular setting, if two geodesics translates are parallel, they exactly coincide. Then it's the same element. So in a general setting, I'm going to say they are not parallel to each other. But anyway, so each projection A to Y and B to Y just finite number and then just two sets, so it's going to be a finite number. There is no uniform bound on this number, okay? But it's still finite, some number. Okay, then we have the following property on those numbers. First, this is always the symmetry. Well, this is obvious by definition because if you switch, it doesn't matter. And two, triangle inequality. If you have a third one here, you always have this. Of course, whenever I write this, I assume that B and C are not equal to Y. So in this case, A, B, C not equal to Y. And then you have this triangle inequality. It's obvious because so each one defines a subset on the geodesic Y, and so this is it, just obvious. This is a triangle. And there are two more things I like to claim, and the rest, the two is not too obvious as those first two, but exist C such that for any triple we have this kind of inequality. Well, this Y I should have used C, but maybe it didn't. So the claim is the constant C, so that for any ABC, the projection with this diameter, one of them is at least not so big. Okay. This is I'm going to explain why this is true after I finish the last property. Such the number C, which has projection, is finite. Okay. So this is a claim. So those four properties are true. Okay. So let me, well, those 3 and 4 basically by the same reason. But let me, for example, maybe explain which one first. Okay, maybe 4.
So for Y, you choose one axis for each problem is class?
Yeah, well, yes, I will do that, but I'm still talking about this example. Yes, eventually I will do that. So maybe 4 was actually maybe let's do it in order 3. Okay, so suppose suppose the projection of A and B is large. So you have C here, and the projection from A to B is large. That means roughly speaking, projection of A to C and projection of B to C are far away from each other. So general picture is like you have A here and you have projection like this. So this is a projection of A to C, or maybe they stay close for a while, and this is a projection of B to C. Okay. Or maybe it's also far away and the projection is nearly 1 point. So this is the picture. Well, I haven't chosen C yet. This is a picture. And what I know is that although they may stay close for a while, this number is bounded by L because of this bounded projection. Okay? But the function says this is large. Okay? That means, of course, those projection sets are disjoint. So my claim is now then the projection, well, what do I want to say? Projection of A C to B is small. So what is the projection of A and C to B? Well, the projection of A to B is this point. Okay. So imagine you are in the tree, or the hyperbolic. I mean, the easiest example, if you're familiar to, is a tree. So if this is a tree, the projection of A to B is really just this point, one point. Okay. And the projection of C to B is this segment. Okay. Therefore, this is small as say comparable to L, which is a fixed number. Let me do it again. In delta hyperbolic geometry, projection A to B, there's some geodesic, but the projection is going to look like this by thin triangle property. So what I want to say is this is around this is more or less the projection of the. Therefore, we have this property. Of course, in this picture, also the projection of B and C is small too. Okay. So this is going to be C. Oh, okay. In the tree, this is really obvious because as long as we have, yeah. So I hope this is convincing for you. So this constant C is more comparable to L. Of course, depends on like delta 2. So this is the end of the explanation for the proof of 3. Okay. Well, maybe I also write. So this is, yeah, okay. This is also nearly the projection of B, C to B. Alright, I changed the viewpoint of this picture. When the projection of A and B to C is large, that's when the whole picture is true. Okay. So now let me write it this way. So in the hyperbolic geometry, if you have two geodesics, translates, which are not parallel, then more or less there's a unique segment from A to B, the shortest one. This is the shortest segment. This is around the point, the projection of A to B, and this is more or less the projection of B to A. Okay. So, well, since the diameter of this is uniformly bounded, so let's write it like a point. Okay. So this is the shortest segment. In this picture, this shortest segment is here. This is the shortest segment. And for C, the projection of A and B to C large means C come close to this red segment for a long time. Then you have a large projection of A and B to C. This is the only way for you to have A and B have a large projection to C. Okay? and if you also see another C here, then it has a large projection. Pi C. Okay. And now, so I'm trying to explain 4. So you are given A and B, which are not parallel. So you have a shortest segment, more or less, uniquely. And now you look for translate C, which stay close to this red segment for a long time. And do you have infinitely many of them? Well, it's impossible because remember you have a bounded projection between different C's, so C1 and C2. Therefore, it's impossible for them to stay close each other for a long time either. So they are nearly disjoint from each other. And now it's a fixed segment, so you see only finitely many of those. So maybe there is some overlap, but that's only bounded distance, bounded length. So you get this claim. If you don't understand the argument very well, then try to draw a tree and draw in 2 straight line and draw this kind of picture. Then try to show something, and the same thing for the hyperbolic space or hyperbolic plane. Okay, so I don't know how convincing it was, but for this particular example, those 4 things are true, and what I was really using is this bounded projection property and hyperbolicity of the space. Okay, so as some pointed out, this is true not only for the action on hyperbolic plane, but also a group action on the hyperbolic space with one WPD element. So maybe I just write it as a proposition. Okay. G is acting on the hyperbolic space and fix hyperbolic and WPD element axis gamma, and I look at all translates gamma, but now I have to divide by these parallel things. So this is, if they are parallel, then I just regard it as just one point. Then I can talk about the projection. So define well, of course, to be precise, so this is no more just a gamma, but a given as class, so I should put like this. But since it's annoying, I don't do that. And also, I mean, this is not precisely determined, maybe after some bounded error, but I just disregarded that either, and I defined this projection the same way as before. Then 1 and 4 satisfied. Okay. Exactly the same reason I explained. What I was using here is just the hyperbolic geometry and bounded projection. And so example is like, for example, so mapping class group acting on a complex, and you fix one pseudo of elements, then as I explained, the action of G is WPD, therefore this applies to the setting. Yeah, so okay. Another more basic example is that if G is one hyperbolic, which I mentioned, namely Cayley graph is delta hyperbolic, then it canonically acts on the Cayley graph by isometries, and it is known that hyperbolic isometry on the Cayley graph is if and only if this is a non-Taussian element. So take any G, infinite order, then this is hyperbolic isometry, and by the way, the action of the group G on the Cayley graph is proper. So you need WPD, is always proper. So if you fix any order of infinite element and then it has axis, then you apply this construction and you get 1, 2, 3, 4. Okay. And this example was since pi 1 of the hyperbolic surface is about hyperbolic, so you could have applied this construction too. So, but my point is that maybe it's different, although, I mean, so if I apply, what is the point? My point is that, so even for the same group G, if action is different, then you get different things, so. Okay. Oh, I have only 3 minutes. Okay, so how do I finish? So I haven't managed to, well, maybe, in say maybe 5 minutes I'm going to define a quasi-tree. So fix a large enough constant, K0, okay. And then define this yk of x z as all elements in y which has a large projection. So maybe I should say the goal, okay? My goal is construct a graph whose vertices are the set y. Okay. This is my goal, okay? So this is my vertices set. So it's like a curve complex. In the curve complex, the vertex is a single closed curve, but in my complex I'm going to construct the vertices are the set of translates of the geodesic axis. So now I have to say when I join 2 of them. So how to join? Okay, in the case of curve complex, you join them if they are disjoint. So join x and z if yk xz is empty. The theorem is this, and I get a graph pky. Depending on the constant k, so you don't know yet that this graph is going to be connected. This is the theorem that is here. It's been drawn by myself that for large k, this 1 to 4 implies pky is a quasi-tree, namely quasi-isometric to a simplicial tree. Okay. So this is a theorem. It looks bizarre, but this is what we have shown. Okay, so tomorrow I'm going to say more about this. I start reviewing this thing, but this is a construction. If there is, so I usually say there is nothing in between x and z, I join. Otherwise, I don't. For example, so let me just write the picture for you. So you have many translates like this, right? So when do I join? Well, if I it's not easy. When how to say? So let me just like this way. Okay. If this is x and z, then remember this is a segment, shortest segment, and this geodesic translate seems to come close to this one for a long time. That means this one is going to be between x and z. Therefore, I don't join those x and z. But if I don't see anything between this and this, I join in my graph. Okay. So once I join like this, and the claim is that this graph is going to be a quasi-tree. I just want to emphasize that in my quasi-tree, this translate to geodesic becomes a point. I only see this yellow line, yellow edges I add. Okay, that's a little bit confusing part. Okay, so I stop here.